So we will start now. So this school, you must have seen the advertisement and also the brochure. This is dedicated to use of atomic force microscope in biomedical and life science research. And so we will take few examples of the at the frontiers where exactly AFM is used in biomedical and life science research. But before we go there, the idea is to give you a complete understanding of what this tool is, how this was invented, what are the technical challenges in developing newer modes of operation or whatever, and then in maybe after a day or so, today's day will be mostly dedicated to understanding AFM thoroughly, and the demo session also for today will be for just looking at AFM, how it operates, how it is done, not for life sciences in general. And then tomorrow and day after tomorrow and 3 more days, demonstrations will largely focus on applications of AFM in biological research. Okay, so that's what the rough thing is. If you have a look at the schedule, you will also be able to figure it out. Okay, so this one I have titled as Atomic Force Microscopy, Imaging on Beyond, because this talk I always keep ready for many workshops, schools, and wherever I need to introduce AFM as a tool. So this will also cover some bit of history of AFM and also various imaging modes. And beyond imaging, and particularly in life sciences, imaging, yes, of course, it's important, but single molecular interaction using atomic force microscope is something beyond imaging. And so this one I have titled as AFM Imaging and Beyond, its invention, applications, and we'll, if time permits, today's 3 lectures, we'll also talk about some future in AFM technology, where all it is going. Okay, so the whole thing begins with 1959 lecture by Richard Feynman. You, of course, all of you know Feynman, right? Famous physicist. And in this lecture that is titled as there is a plenty of room at the bottom. And this is the lecture people always use for nanotechnology topics, right? And a lot of physics at the scale of nanometers was focused, was basically discussed in this lecture. But I picked up 2 paragraphs which are of relevance to what we are going to discuss further today. This paragraph says, if I have written a code as in like memory, back then it was called memory, with 5 times 5 times 5 atoms to a bit, that bit is a 1 memory piece. The question is, how could I read it today, even if you are able to write it? The electron microscope is not quite good enough. With the greatest care and effort, it can only resolve about 10 angstroms, that's 1 nanometer, and that's with greatest care and resolve. I would like to try and impress upon you, while I am talking about all those things on a small scale, the importance of improving the electron microscope by 100 times. So it should be possible to see individual atoms, and what good would it be to see individual atoms distinctly, and then it goes on listing what all is possibility. So what Feynman is stressing in 1959 lecture is that the best microscopes of the day, electron microscope of the time, was not does not have resolution enough to see things at 1 nanometer. Okay, so that is one thing. The microscopy in general, optical microscopy or electron microscopy or whatever microscopes were there at the moment, were not able to see things at 1 nanometer resolution. That's the thing, because and we'll come to that why this was not possible at the time. And then he goes on listing things that are possible if you have a microscope like this. And he says, what are the most central and fundamental problems of biology today? This is quite relevant for today's topic, right? Atomic force microscope for biology applications. There are questions like, what is the sequence of bases in the DNA? What happens when you have a mutation? Many of these problems now are solved. So it's 1959, please note that. How is the base order in DNA connected to the order of amino acids in protein? What is the structure of RNA, which is of course we know now? Is it single chain or double chain, and how is it related in its order of bases to the DNA? What is the organization of microsomes? How are proteins synthesized? All these problems are solved now, yes, but these are the questions in front of Feynman in 59. Where does the RNA go? How does it sit? Where do the proteins sit? Where do the amino acids go in? So these are all the functional details about inside a cell. In photosynthesis, where is the chlorophyll? How is it arranged? Where are the carotenoids involved in this thing? What is the system of the conversion of light into chemical energy? For a physicist, these are really frontier problems or cutting edge problems in biology that he is sort of telling to the students in this lecture that he gave at Caltech. So let's then look at more carefully what did he mean by all of this. Okay. So if you see, and I call this title them as beam microscopes. We never call beam microscope as such. We always call atomic force microscope, then scanning near field optical microscope, also STM. All of these are termed ion conductance microscope. All these microscopes are called probe microscope, the general category of probe microscopes. And before probe microscopes came, there were beam microscopes. Okay. And they are still around, of course, they are very powerful. They have also progressed over years. And beam microscopy involves use of beam, be it of a light beam, be it X-ray or some electromagnetic wave, or it could also be electron or ion or some such thing, some particles. So, but it's still a beam of particles. And what do we mean by beam? That the source of this beam, or source of electrons or ions or whatever, is sitting far away, or light, for instance, is sitting far away from the specimen that is to be imaged. Okay, so there is a beam of light or electron or whatever that falls on the specimen. So in that way, it's a beam microscope. So what is the limitation or resolution of this beam microscopes using optical microscopes, which is basically, I am taking example here of a confocal microscope, and whatever you do, and now there is STAID and many other tools which have progressed to the level of single molecule resolution. But back in the days, or even decade ago, 2 decades ago, this was what the confocal microscope was, the best optical microscope that was there, and you couldn't see things which are smaller than this D, which is about numerical aperture and 1.22. These are called a base criteria of resolving two spots on a, let's say, on object. And clearly you can see here that the wavelength of light that's being used is limiting the resolution along with the numerical aperture of the lens. For instance, you can use numerical aperture which is very large, and you can make a lens that is maybe the size of this room, and astronomy people do that, but that is not really feasible to do a tabletop experiment, microscopic experiment. So numerical aperture cannot be increased beyond a point. Okay, and typically we all know, if you are working in a biology lab or in general microscopes, we know this is really limited by 1.3, 1.2, something like that. And for a microscope that uses fluorescence and other things, it has to be within a visible range. So lambda is restricted to visible range of light, and this then translates to something of the order of little smaller, let's say, than half the wavelength. So if I use like 500 nanometers of wavelength in the center of the visible band, then your resolution cannot be better than about 200 or 250 nanometers. Okay, this is a routine thing. Many times this is much worse than that because you haven't aligned or focused it properly and things like that. But best care and effort, as Feynman said, will lead you to resolution that is of the order of 200 nanometers, far 2 orders more than what we want in Feynman's lecture, which is said 1 nanometer would be the desired limit of resolution, right. Now then, Ernst Ruska and the team of researchers, they built electron microscope, and the idea, you can just go from here to there. The idea is simple. Now what is the limiting factor here? This is numerical aperture and the wavelength of light. Numerical aperture is about lenses that you use, and wavelength is of the beam. There, if you then use electron beam and increase its energy, so its wavelength can go down. This is what quantum mechanics told us, right? The de Broglie hypothesis, that the wavelength of light is determined by the kinetic energy that the electrons have, and faster the electron is moving, tighter its localization it is, and it is sort of giving you a smaller wavelength. So you can use electrons with high energies, and then the lambda can go down, and you can use lenses which are now electromagnetic lenses, because the electron beam can be tightly focused or not so tightly focused, will depend on how well you can focus it using electromagnetic lenses as opposed to optical lensing. And with that, people pushed its limit, and one could get 10 nanometers to 100 nanometers once again. 100 nanometers was a really badly sort of arranged scanning electron microscope, but 10 nanometers was quite possible. And now, of course, the transmission electron microscope and other things are giving you resolution which are at the scale of atoms, but that's very recent development. This wasn't there a couple of decades ago, particularly in the 80s and 90s, where STM AFM was invented. So that's the problem that Feynman sort of outlined in one paragraph. That's the basic reason behind your microscopes not having good enough resolution. Okay, and that's the Abbe's criteria, which is a famous one. So before AFM, STM, and all these tools were invented, there was another microscope in between, and these are called field iron microscopes. And I'm mentioning this because I did my master's thesis building one microscope of this kind in Pune University. So the idea is you're not able to image things when they are flat, but this microscope could image objects which are sharp. And you can see this is a FIM tip, and tip will come to AFM business quite often. But interesting thing is that this is the first microscope which uses a tip. Okay, and this tip, as you can see, you're depicting it as one atom is seen. So at the very front, only 4 atoms are sitting. You see, so it's atomically sharp tip in a way. And if you make the object so sharp and you apply high voltage to it, then the electric field, this is some basic physics, if you make a sharp object and put some potential on it, the electric field at the very tip is intense, really high. And so that way the electric field at the very end of the tip becomes extremely high. And in electron microscopes, actually scanning electron microscope, SCM, that we saw, such tip is used as a source of electrons. If you have such a high field at the very end of the tip, you can strip electrons from that material, and that becomes the source of electron. Okay, so that's the field emitted electron source. But what is done here is that you sort of make such a tip, and you pump out the whole thing, the air or the gas is taken out, and then you fill this whole chamber with the polarized gas atoms, or gas atoms that can be polarized. So there are atoms which are spherically symmetric. If the shells are all completely filled, there is nothing like extra 1 or 2 or whatever, then these are very difficult to ionize, right? But they get polarized. If you place them under a large electric field, their charge centers will sort of displace, and you will get a polarized atom, but not ion. Okay, so such argon, for instance, or many such xenon and all those things have such nice spherical symmetry. And these polarized gas atoms, once you put in extremely high electric field between the screen and the tip, one could sort of have a polarized gas atoms inside. And once that is polarized, it is pulled towards the tip. Okay, and they have thermal energy, so they are going around with a lot of kinetic energy, which is thermal. And once they hit the tip, which is again cooled down to about 20 to 100 kelvins, about liquid nitrogen or liquid helium temperatures even. And once you have them cool down, this polarized gas atom, when it hits the tip, it will lose some of its kinetic energy. It will actually get, it will cool down. It will lose its momentum and all. And but that's still not enough that it comes to a rest. So you can have a couple of jumps like this, depending on how much it has lost the energy, how long it sat there and stuff like that. And depending on that, this gas atom finally will come to rest. But moment it comes to rest, then something called tunneling occurs. Tunneling is the physics phenomenon where there's a barrier, an electron can cross the barrier without going over it. That's called tunneling. All right, so this gas atom that finally comes to rest, the tunneling occurs and it gives one electron to the tip. So now it's positively charged, and this tip is sitting on, again it's in a positive in terms of, the tip is sitting at a positive voltage, and the tunneling occurs, and the tip, both of them are positively charged now in a positive way, and this, then the atom is repelled from the tip and goes and strikes the screen and carries the information from where it came. All right. So many such atoms will do a projection of a tip on the screen, and these are actually the bright spots that you see on the screen is a projection of a hyperboloid on a plane, hyperboloid tip on a plane, and this is how first time ever mankind saw the atoms. Okay, and this is the and the Muller who first did this says atom still hides from a casual sight seer. This is a very famous quote, because it's hard to do, very difficult to do. I did this in my master, so I know how hard it was to build, and low temperatures, ultra high vacuums and things like that, and the phosphor screen, all of this we could get images of atoms, and that was the in between thing. The real paradigm shift in microscopy business came with this microscope called scanning tunneling microscope, and why I refer to iron microscope, because the first time the tip was used, and these people actually cleverly used the tip once again, but this time not sitting far away, like few millimeters away from the screen where the tip is actually imaged. They are using now, instead of electron or a light beam, they are using a tip as something that can be used to map the surface. Okay, and let's see how this is done. So this extremely sharp, atomically sharp tip, and the ways to make this. This is the tip that we have made in our lab, tungsten tip, maybe 98, 99, and this kind of a tip is mounted on a tripod design, which is basically X, Y, and Z piezo stack. This piezos are, you know what piezoelectricity is, right? Everyone knows, or yeah, to some extent. Piezoelectricity is you apply voltage and it expands, but you apply like 10 volts or 100 volts and it expands by an angstrom or two. So it's extremely precise in terms of movement. So you can actually mount this tip on a tripod like this, apply 3 different voltage amplifiers, apply voltages on three of these, and essentially what you can do with the servo control and all that, we'll talk about it. You can bring the tip down close to the surface, and you don't allow the tip to touch the surface. So this is another technological marvel that these people in IBM Almaden achieved, not Almaden, IBM Zurich achieved, got Nobel Prize in the end. So they took the tip, mounted on a tripod like this, and slowly approached and took it all the way close to the surface, but not quite touching. It's just sitting like an angstrom or two away. This is a hard thing to do, because as I am talking, this table is, because of my talking, this thing is shaking by microns. Okay, I walk around and this room is shaking by tens of microns. And what we are talking here is holding a tip about an angstrom or two away without touching. That means all this vibration should not reach the junction where all this is held together. So this is quite hard thing to do. And so here you mount it on a tripod design and you bring it all the way down to 2 angstroms, and moment you come that close, the electrons from the tip and from the sample sort of don't know, do they belong to tip or belong to the sample, right? The wavelength spans over couple of angstroms, over a nanometer, and this is again once again a phenomenon called tunneling. So apply a small bias between tip and sample, about 100 millivolts or so, even small, 10 millivolts also is good, and then the without touching current starts to flow. Normally we know that the current flows when you have a continuous thing that goes from one to another, right? Without touching, now the current starts to flow, and this current is called tunneling current. There is no classical analog for tunneling, you are all aware. Only electrons can do this job. They are quantum mechanical particles. So so then the current starts to flow, and one interesting thing about tunneling, if you really look at the textbooks in physics, is that as you go little away from the surface, it falls rapidly. So, if you are at 1 angstrom from the surface, the tunneling current would be somewhere close to 10 picoamperes, let us say. You go 2 angstroms, it will fall to 1 picoampere, and you go to 3 angstroms, it will become 0 almost, and it's femtoamperes, not detectable. So, it's extremely sensitive to this vertical position of the tip, and that's what gives STM its fantastic resolution. What then happens is that if you have a tip that is like this front atom here, if the front atom is sitting angstrom closer, 1 or 2 angstroms closer to the surface than the back 2 atoms, right? The 3 atoms sitting at the at the back compared to the front atom are 2 angstroms away compared to the front one, and as I said, the 2 angstrom away, the current has dropped so much that 1 angstrom away is most dominant, and this is what gives STM the atomic resolution. Just one atom interacting with the surface effectively, okay, and that's sort of, then if you take this sharp tip and scan over the surface, if you are sitting on atom, current is high, in between atoms the current is less, and because it's just one atom interacting with the surface, this happens, okay, and then you go over the atom again, the current is again high, and you go on scanning the tip over the row of atoms, go to the next row, and this way you can do raster scanning by the XY piezo elements on the top, and you can generate topography of flat surfaces now. Okay. Problem with ion microscope was that you have to make the thing that has to be imaged had to be made into tip, and how many things you can make tip which is atomically sharp? Actually 1 or 2 elements. Tungsten is very famous, that also there is a lot of material science in how you pull the tungsten. Tungsten is brittle, but you pull it along one direction, that is ductile, then you make a wire out of it. So, you know exactly along 111 plane you have the tip, and then you etch it and all that thing happens. But normally if you try to do this with gold, with many other things, does not work, etching process and the way we make the tip. So, the ion microscope, okay, the one that we talked before, it imaged the tip itself and not the specimen, right? And there was no specimen actually, only tip, and the atoms which the polarized gas atoms which sat on the tip were finally were kind of your mean of imaging that. Here the tip itself is used as a imaging object. So, just like beam microscopes use optical or electron beam, electromagnetic or electron or ion beam for imaging, probe microscopy uses probe for imaging, and that is the paradigm shift in the whole microscopy business, okay, and they were awarded Nobel Prize right after the invention of STM. So this is STM, and why are we talking about STM? Because AFM came just after that. This is topograph finer, we should not really spend time on this, but in 1986 this is a paper in PRL, and I put the abstract here. Let us read the abstract so that we know what is the context now this is done. The scanning tunneling microscope is proposed as a method to measure force. What they have done here is that you got the same tip and same sample, but now what we have done is mounted the tip on something called a cantilever. Okay. So, before there was just the tip that is sitting on a tripod, now what you have is a tip sitting on a cantilever, and then this cantilever can bend with forces, okay, that is that the tip the front end atom will experience. And so, as how do you measure that bending? How does one see how much it bent down by? What you do, you place another tip which is STM on back of the cantilever, and we know that if the distance between the surface that is bending, it changes, the current drops rapidly. So, the tunneling itself is used as a method to find out how much the cantilever bent by. Okay. So, how did they think about this? Why did they think about this? What was the reason for the invention of AFM? And if you look into the history, they were questioned a lot by community as to if this is then shown also with a nice picture here. If I have to bring a tip atom close to the surface atom is bound to the whole thing, yes, fine, but then this binding also is depicted by a spring here, you see. So the questions that was raised, and one gentleman, who John Pathika, who really insisted on this question, is that we are thinking that the STM tip and this substrate as a rigid continuum bodies, but at the scale of atoms this is not so. So what's going to happen is that this atom from the tip is going to get pulled towards the sample, or the sample atom or the substrate atom will get pulled towards the tip, and how can one ensure then the separation between them? Okay. This was a fundamental, I mean, it seems very obvious thing to ask, and this is what John Patika kept on asking the team from IBM Zurich, what really happened in first few conferences where STM was just getting popular around the world. And so then they went back to the lab and said, okay, fine, if this is the case, let's measure how much force your tip is feeling, right? And to measure that, they mounted a tip, which is a diamond tip, on a gold foil lever, and this diamond tip is now, because diamond cannot be made into atomically sharp, of course, it's problematic. But then what they could do by doing it this way, they could actually measure atomic state. So at the, on a surface, if you know this surface physics a little bit, there's never atomically smooth all over, except for mica, let's say, or graphite. Other things have one atom step, then second, and the third, and some. So there are atomic steps on the surface. Nothing is atomically smooth ever. And then they managed to image one step, which is what is shown in the thing here. And this is how AFM was invented. The other advantage of doing it this way was that STM was limited only to metal surfaces, right? But you need free electrons for tunneling to occur, or at least you need a band structure like silicon or semiconductors will provide you. This band structure or the free electrons will provide tunneling, and that's what is used for imaging. So it means that STM can only do conducting and semiconducting surfaces, topography. They do get pulled, and later later people realize, but that the amount by they get pulled up is extremely small. Okay, so this is essentially two atoms will have a Lennard-Jones potential, right? But that's only when they're two atoms. If they're sitting on a background of a tip and the substrate, they don't remain Lennard-Jones anymore. So this is sort of they're more tightly bound to the thing. And then again, for very high resolution AFM pictures, people cool it down to to the Kelvin temp, 1 Kelvin or 3 Kelvin, which is liquid helium temperatures, or at least liquid nitrogen temperatures. So this means that their binding is even sort of stronger with each other in a way. There are no thermal motions in the whole thing. Okay, so this is how AFM was invented. So this is the invention history of AFM, and then this naturally took care of the fact that yes, we can now image non-conducting surfaces. I can image oxides, we can image anything, and no one thought of biology back then, because these are all very, very rigid things. No? You want them to be the Young's modulus of both the substrate and the cantilever material, whatever, should be in gigapascals and more. So they are, and the AFM for life sciences, we are dealing with materials which are extremely low Young's modulus, of the order of kilopascals even. Okay, 6 orders of magnitude smaller. So this is still restricted to non-conducting samples, but with high Young's modulus. Now, I mean, this is the first AFM cantilever that I made myself in my PhD, and just like they used the diamond tip, I didn't use diamond tip because I wanted to look at some electrostatic interactions and mounted a mirror on the back. This was done just by some plier and tools in the lab, and this actually worked well. Initial few days, but it's quite bulky, as you can see. I don't have a scale bar there. Yeah, millimeters. So this is like a 2 millimeter long cantilever. Okay, and we'll see in coming further in the lecture that this is not anymore the case. The cantilevers are extremely small objects, microfabricated, but this is what we did back then, because the commercial cantilevers were not so much in, they were there already. the Olympus cantilevers were there. Many companies in California had cantilevers, but somehow we didn't have access to these cantilevers back then. So we started making our own. And first 3-4 papers in my PhD, we actually used these cantilevers to, yeah. Yes. Yes. So, I mean, to tell you how it was done, we went to the goldsmith, bought some gold, made a thin wire out of it, about 10, 20 micron to 80 micron different. I mean, they couldn't really do it with the precision, but extremely thin that you could barely see with the eye. And then these thin wires, I passed them through a ruling mill with a high pressure and flattened them out. And these flattened things are and then cut them with a normal scissor and put a mirror on it and bent it, and it worked. And shine a laser on back and everything, which was done in 1998 from Pune University. Okay, but now this is the real thing. This kind of cantilevers are not really great. They can do some force measurement, but not great for imaging and for various other things. Okay, and this is where we start our real AFM business. So it's around 10. Okay, we have break at 10:30. No, 10:20. 10:20. So 10 more minutes. So we'll just talk about what cantilevers are in AFM. The very first AFM was cantilever, also was made out of gold foil with a diamond tip attached to it, and I said that they are not really great. Okay, you can use force, you can measure forces with great resolution, but not good for imaging largely. As you can see from the first image also, it wasn't great. So in the last paragraph of this paper, and I will really invite you or urge you to read this paper. This is really nice paper. I read it in my PhD. This is in paper and its title also Atomic Force Microscope. Last paragraph of this paper talks about problems of what they have done that moment, and this is the problem. The problem is, if I use some cantilever is a complex object. It's not just a spring to measure forces. Normally forces are measured using spring. This is a common knowledge, right? And even now in AFM and everywhere, optical tweezers also measure forces using a spring in the end. But that spring has to be extremely weak. Okay, why this is to be so? What is typical stiffness of a spring that you are used to? Let's say I have to weigh 1 kilo of sugar or salt or onion or whatever. 1 kilo means how much force? I will keep asking this, otherwise you will fall asleep. 1 kilo is how much force? Anyone can say? 1 kilo weight is how much force? Kilo is mass, no? It's just 1 kilo mass. Huh? Yeah, you have to multiply. Let's say 10 or 9.8 is 10. It's close to 10. So 1 kilo will be 10 newtons of force, right? 10 Newton force is quite. So our weight is about 100 kilos. So our actual force that we exert on the ground is multiplied by 10. Okay. So 1 kilo of, say, with a spring balance, if you attach 1 kilo weight, it will move by millimeters, no, or at least a centimeter or so. So that you can say this is 1 kilo, it's moved by centimeter, and then on the centimeter you can have 10 more scales. So you can say even in 100 grams or whatever. So so that has to move by a centimeter at least. So you can make this calculation: 10 Newton of force. If it has to move by a centimeter, then what is the force constant? It will be some about say 0.1 or millinewton per meter or 0.1 Newton per meter, in that range, right? So roughly. So no, not that. 10 raised to 6 Newton per meter or something, because you have centimeter and 10. Right? So 10 raised to 4, let's say 10 raised to 4 to 10 raised to 6. That is the range of spring constant that one is used to, which is sort of used to measure forces which are large, 10 Newton or 100 Newton or things like that. Okay, and that's a force constant of 10 raised to 5 at least Newton per meter. Now then think about forces which are billion times smaller. Okay, they are at least nanonewtons, 10 raised to minus 9 newtons or 10 raised to minus 12 newtons. Okay, so it's billion or 1000 billion times small force, because two atoms, let's say, when interacting, if you really work this out, Lennard-Jones amount of force, this will turn out to be a few piconewton to nanonewton range. So the force is small, the cantilever has to be, it cannot be 10 raised to 6. No, if I have a 10 raised to 6 or 10 raised to 5 Newton per meter cantilever, and I have got 1 nanonewton of force, it will move by a nanometer. It will not even move by a nanometer. It will really be a small, small bending or small stretch of the spring. So the spring has to be extremely weak. And how weak? Roughly one can say from this Hooke's law, which is what we are doing right now, is if I have 1 nanonewton of force, and let's say through interferometry, through some optical detection technique, which is technologically quite high end, I am able to somehow measure stretch in the spring or bending of the spring of the order of 1 nanometer. Okay, so if I have 1 nanometer detection technique, which will come to how that is done, if I am able to detect 1 nanometer of cantilevers or the springs movement or stretch, and if I am going to measure 1 nanonewton of force, then the cantilever stiffness has to be about a Newton per meter, right? 1 nanonewton, 1 nanometer. Okay, so your spring constant has to be about a Newton per meter. Now this seems like Newton per meter, so but that's not a, that's very weak. Okay, because as we just said, the typical springs that one encounters in daily life are 6 to 7 orders more in stiffness. Okay, so once I have to make a cantilever that's very weak, and if I look at this cantilever, how did I choose these dimensions? What was my logic behind choosing these dimensions? And the logic is simple. If I use some, I will write it down here. So for instance, I aim to get 1 Newton per meter stiffness. So my K should be about 1 Newton per meter. This is visible to everyone? This is not coming in the way, no? Yeah. So this is what I desire to get. And how do I sort of go about doing this? So for cantilever, which is this object with some length, thickness and breadth, the formula, let's say, which comes from, I will also explain where it comes from. So that's breadth of this thing, h is the thickness of the cantilever and L is its length. Okay, so width, thickness, and that's length. So you can clearly see, if I make it long, it will be floppy. If I make thin, also of course it will be floppy, and also if it's not too wide, also will be this the thickness has to be as possible, length has to be as long as possible. So one can play with this. So if I put this to be millimeters, and this thickness is to be brought into microns or something, I can put these numbers and use Young's modulus of gold. E is Young's modulus, and you can sort of roughly work out how much stiffness. And this cantilever was about 1 Newton per meter, and this is a big cantilever. One can see with eye and everything. There's nothing odd about it. So you can put this. Well, typically stiffness of this is some bit of a civil engineering or mechanical engineering. If I have a beam, cantilever beams are quite common in civil engineering. So if I have a beam, and if it has to be, attach a weight at the end and it bends down, how much it bends down by, with what stiffness it will have for given amount of weight, how much bending it will cause. This is done by a flexure equation. It's called flexure the length of the beam, Young's modulus of the beam, and this is the cross section's area moment of inertia, which happens to be BH cube upon L square in a rectangular cross section things which has to bend around this particular axis or that axis. So that's the reason why cantilever stiffness is determined this way. What this ignores is the tip at the end, of course the mass at the end, all of that is ignored. So, it is just rough estimate, it is not really accurate one, we will come to that in a second lecture. So, use something like this and get 1 Newton per meter, and 1 Newton per meter, if I have a detection tool to measure about a nanometer displacement or a bending, I can measure 1 nano Newton of force. Okay. So, this is the idea. Now, what this means is that I want to push this K down as low as possible. Stiffness has to go down and down and down in order to measure 1 nanonewton. Then someone says 1 nanonewton is always not the case. Piconewton is what optical tweezers and a lot of techniques, even including AFM, measures piconewton now. So, 1 nanonewton is not the thing to measure, right? It can also go down, and this means that you have to push the stiffness of the cantilever down and down. Okay. So, as low as the stiffness is better, but then there is a problem, and the problem is following. If I idealize the cantilever as a massless spring, which is also a super simple oversimplified assumption, because what we have is a cantilever with that thing with a tip attached. What I am going to say is that this actually is nothing much but a spring and a point mass, massless spring and a point mass. We are used to that in physics, right? We always say, well, spring and a mass m with a spring constant k, and the frequency of resonance frequency of this will be root k by m and all that we sort of know. So, even if we make this oversimplified picture of a cantilever, the spring will have a resonance occurring at given by roughly by this root k by m. M is the mass, which is effective mass of the whole cantilever now. Okay. So, and there could be m star written as there. Resonance would be, suppose I take the spring and drive it, and then it will and then you plot the amplitude. Okay, we have that long thing, meter scale. Can you see a meter scale somewhere? Long 1 meter scale. So, suppose I take a or simple scale also, something that vibrates. So, you start moving it, it will have a large amplitude for a small movement, right. You can also do this, or you can also do a rapid movement and the amplitude becomes more, right. This happens all the time in resonance. So, if I look at the amplitude at the tip versus frequency of driving, you will see this. This is the resonance curve. This is, everyone is okay with this, everyone is fine, and this frequency is your f0 or f, that is what it is. Okay. So, if I take a spring and drive this with a drive the spring like take a cantilever, bang it, it will start oscillating on its resonance and then slowly die out. But if you start oscillating it continuously, the amplitude will be largest at one frequency, that is resonance frequency. And so, this is given by root k by m. This is 12th standard physics. Now, see what happens if I have a 1 millimeter long object. If I start increasing length of the cantilever, the weight increases, the mass increases. Thickness has, of course, no problem. Smaller the thickness, the better in a way. But that does not increase the mass, reduces, but the length of the cantilever is problematic. You start increasing, and you see the k changes a lot with L. It's a cubic. So, resonance is simply this. You do this of resonance. This is resonance. I am just shaking it faster, and then amplitude just goes up. This is happening at resonance. Okay. And if you take a longer one, you can see other modes also, higher eigen modes and things. So, what's the problem? What's the problem? Why am I saying all of this? Because I am taking this cantilever over the surface, okay, and it goes from one point to another sensing force, and if the cantilever's frequency or its rate at which you will respond to the change in force if you have a sluggish cantilever with lot of mass, it will not respond as quickly to change in force as opposed to a small mass cantilevers, and that's characterized by inverse of the resonance frequency in a way, roughly. So, if the cantilever's resonance frequency is high, that means it quickly will respond to force, it is not sluggish, it does not have too much mass. So, force changes over the atom to in between atoms or over atomic step to lower atomic step, from here to there. Suppose I bring a cantilever, sense of force there and sense of force there, then the force there is lower than here at the same height, right, and that you raster scan the tip from high force to low force region. The cantilever has to respond to that change in force in a quick enough time. If that takes 1 second, then what happens? I go from one spot to another spot 1 second, third spot 2 seconds. The whole line scan, if I do 256 points, which is normally digital cards do, or 512 points, 500 seconds for one line, and then you do 500 such lines on the other side. So, that means 512 into 512 seconds, that is basically your entire PhD time, okay, maybe. So, this is extremely slow, okay, and this happens because the cantilever's response time has gone down because it is too much of inertia, too much of mass on the cantilever. So, yes, if you push down k, the F goes down, and if you push down mass, also F goes up. Okay. So, one has to do this. We want a smaller and smaller force constant. This small force constant will push the frequency down because of this consideration. The mass has to be more, longer and longer cantilever, and at the same time mass becomes too much, this becomes also slow. So, you need to have a cantilever that is small in mass, not that long, and that exactly is what the problem that is stated in the last paragraph of this PRL paper, and they also say, but that is okay, that is not a problem, because we are just beginning to do this. They then said, look at the IC industry, integrated chips, okay, and integrated chips for that time were making designs and making small objects using focused ion beam and whatever the chip technology, microfabrication technology, layers of different kind of materials, etch them out and do things in a way that you can make features of the order of 10 microns, 5 microns. One transistor is now today coming down to 100 nanometers even. Okay, but even at the time when AFM was invented, they said, okay, this is a problem with our cantilevers that they use now, also the same one with my cantilever that I used in Pune University, but that is not a serious technological problem. You have a chip industry to get help from, and this is exactly what the people did. Okay, so what is now done is that you have a silicon wafer on which you have got this oxide layer and you got another material and whatever, and you can use the etching technology and whatever, lift it up, all that. This is something beyond me, but by doing all that in one full silicon wafer, you can etch out cantilevers which are in length much small. Okay, about the length of the cantilever now is close to the breadth of your hair. Breadth of your hair is typically 100 micron, and which is about 0.1 millimeters. Okay, and so the whole length of the cantilever can now be brought down to 100 microns. Okay, so this is one cantilever, and with the same technology we can also etch out, also make a pyramidal tip. Okay, and this the whole thing can be one object now. We do not have to attach any diamond or anything. This is a pyramidal tip. There is a cantilever dashboard kind of a cantilever at the back, and you have a chip on which this is the cantilever, okay, and this is the whole chip. Many times you enter into AFM lab and you people think this is a cantilever. That is not cantilever. Cantilever is something that you do not see with bare eye. It has to be seen under microscope. Okay, you never see cantilever with just like that. And that very end, what you see is the cantilever. That SCM picture is being seen on the left. And what we have, when you use the cantilever, the tip sometimes get little dirty. That is what has happened. So one also use the cantilever, see it under microscope to see if this dirt picked up. Yeah. Yes, this is one monolith. So this is the whole cantilever. This thing that protruding out is one material. It's that's important for chip industry. No, it's a monolithic thing. No, one silicon wafer, single crystal. That's something which another technological marvel that we already have in place for something else, and then can be easily used for AFM cantilevers. Okay, so this is the cantilever now, and if you really think about a length which is 100 microns, this whole chip will look something like 3.4 millimeters with a width of 1.6 millimeters, and that's not important because all this is used is a chip which is basically clamped with a spring and held together, and that guy is free for sample to come and approach. And typical lengths are 100 to 200 microns in length, which is 0.1 millimeter. Thickness is few microns, 1 or 2 microns, and width is of the order of 50 microns. So typical dimension of a cantilever, this will be a 50 micron or so. The thickness of this will be 1 or 2 microns, and the length of this will be about 100 to 200 microns. And you can play with this to get different stiffness cantilevers. And that's one advantage of AFM over other tools, is that you can vary the cantilever stiffness by changing the tip, and then there's a big range of stiffness one can choose from. And this is advantage because the kind of interaction you are probing or measuring, if that's a strong force, stiff cantilever is good. Not so strong force, you have to use weak cantilevers. So this kind of maneuvering is possible, or choice is there. Now, these cantilevers, I'm also showing you the other type of cantilevers which are called triangular levers. That's dashboard or a diving board, not dashboard, but a diving board cantilever. Swimming ke time pe hota hai na diving board, that kind of cantilever on the left. And in one chip you can get all these options also. One chip on that thing, and you have this is a quite stiff one, not so stiff, and even weaker. And now what you have is a tip sitting at the very front. I don't know if you are able to see from the front, but it is now, instead of getting clamped over there, it is clamped at two ends, and to reduce the mass you could just have it full, but then removing things from there will reduce the mass. And this is 200 microns, as I said. So this whole length would be 200 microns. Okay. So these are the kind of cantilevers are now used, and the reason why they are so small, people wonder usually working with AFM, cantilever is so tiny. Why should it be so tiny? It should be tiny because if I have too much mass, it will be a sluggish cantilever. Okay, just too much inertia in it, and it will not be respond to change in forces as quickly as it will these small microfabrication cantilevers will respond. Is that clear? Any doubts? Oh, already 10:30. Maybe we can start the next session 10 minutes later. Yes. Okay, this end you're saying. Yes, the silicon cantilevers are pyramidal shaped, and they are somehow made into, yes, they are sharp enough. They sharp as, it can be made as sharp as one atom at the tip. Now the question is, how do you know if it's one atom only? This is difficult, no? How do we see this is only one atom? Moment you start getting atomic resolution with a tip, then it is a one atom tip. But typically what people say is the tip radius. Okay, so tip radius is something, suppose this is my tip, maybe, okay, here, let me wipe this out, duster. So suppose this is my tip, clearly not one atom, and what you do is sort of fit a sort of a circle to it, and this radius, which is called tip radius, or tip I will call it, all, if you go to market and start buying cantilevers, this will be specified at 8 nanometers. This one. Now, does this mean it is sharp atomically? It is difficult to say. It all depends on, suppose I will decorate this with tiny atoms like this. And as I said, if this atom is little bit ahead of the other two atoms, and if it is tunneling, that is okay. You can call this tip as atomically sharp tip, because the other two back atoms are not contributing to tunneling current as much as the front one. So, it is atomically sharp. So, what does it depend on? Not only how it looks, but which phenomenon that you are using for sensing the distance between tip and sample. So, suppose surface is there. So, the front atom 1 angstrom, the other is a bit away, and tunneling current is exponentially falling, which means the front atom is really at the front. Suppose the tunneling current is not exponentially falling, then this tip is not atomically sharp tip. It will, because the other two guys will start contributing to the, the atoms and the back row will also contribute to the measurement of whatever you are. For instance, force is not so sharply varying like tunneling current. So, the same tip would be called atomically sharp for STM, but not atomically sharp for AFM for long range forces like van der Waals and other things. But if you really probing chemical potentials, we will come to that, and that is how AFM gives you atomic scale resolution, which is another topic, and I will, if you are interested, you can read this book called Non-Contact Atomic Force Microscope. It is papers put together, chapters put together. This branch of AFM deals with atomic scale resolution imaging. We are not going to focus on that in this course. Yeah. But it all depends on what interaction you are probing. It is a slowly varying interaction, it is not atomically smooth. If it is extremely exponentially varying interaction, it is atomically sharp, like that. Yeah. This one? Well, this is the cantilever. The probe is just sitting at the end, looking at you. So, it is like that. So, this thing is made. So, I don't know if you can see the probe here, just like a dot, and that is pointing at you, and the whole thing is cantilever. Similarly, you have the probes sitting here, here and here. So, probe as in tip. Okay. So, yeah.
So, cantilever getting attached to the chip. So, how does the force constant of two materials resonate? So, the chip and the cantilever is a different material. So,
No, same material.
same material.
Yeah.
Given that it's made out of same material and attached to that chip, the force constant should be towards the.
Okay, I get your point. So, imagine something like this, and this is extending 3.5 millimeters, right? It is quite big, and the cantilever is there, which is micron thick. This is millimeter in thickness. This guy is like a rigid thing, it does not bend. What bends is this thing only, down. So, it is something which is attached to a rigid thing. So, if I clamp here, let us say, and hold this object in a spring, and I sort of tilt it little bit, which is what is done in AFM, and bring it closer to the surface, it will interact, and this guy only will bend, not this. So, it is the force constant only of this guy, because the force constant of the other guy is almost infinite, and you can say they are in series. So, that means this. No. So, imagine suppose this object which is clamped here, this guy also bends down, is what you are saying, no, compared to that.
It won't bend, but it might not allow that small guy to bend freely.
Oh, no, why not? I am just like holding a small guy like this, it will bend, no? What's the problem? So, suppose I have a cantilever like this, and this guy is held there, and I sense a force, I will bend. Why should this oppose? This is rigid, this is infinitely. If this was also having a low force constant. For instance, if I take a object which can bend itself and I put a tip there, then these two things are the two springs in series. Here also two springs are series, but the one spring is infinitely stiff. So you can think of this one spring and the other spring. What is the effective force constant? Is 1 upon k1 plus, so the lower one will dominate. If this is too high, the total sum of these two will be just the lower one, like kinetic rates and a lot of things. So the big block, the chip of the cantilever doesn't budge, it's just infinitely large in stiffness, so it doesn't matter. Yeah.
One thing is that the other end of the cantilever is free.
Yeah,
That,
yeah. Other end is free, of
yeah,
course.
that is more important. That's the reason.
Then yeah, that's free with the tip on it. So this is the held with the chip at the back. The chip is held with a spring. We'll see that in the lab today. And then this guy is free with a tip there, and this the whole block doesn't bend. Of course, it's too high in stiffness, and this only bends to measure force.